Good day everyone. So today I am going to discuss about the formation of the universe to the formation of the earth. So the first one is the formation of the universe. Before Hubble, most astronomers thought that the universe didn't change. But if the universe expanding, what does this say about where it was in the past? If the universe is expanding, the next logical thought is that in the past it had been smaller. And the beginning of everything, the Big Bang Theory. The Big Bang Theory is the most widely accepted cosmological explanation of how the universe formed. If we start at the present and go back into the past, the universe is contracting, getting smaller and smaller. What is the end result of a contracting universe? According to the Big Bang Theory, the universe began about 13.7 billion years ago. Everything that is now the universe was based in a very small body. Imagine the universe in a single, hot and cold mass. Since the Big Bang began 13.7 billion years ago, the universe has passed through many different phases or epochs. The Big Bang Timeline. The first one is Planck epoch, or also known as Planck era, from 0 to approximately 10 to 43 seconds or 1 Planck time. This is the closest that current physics can get to the absolute beginning of time, and very little can be known about this period. It is hypothesized that the four fundamental forces, electromagnetism, weak nuclear force, strong nuclear force, and gravity, all have the same strength and are possibly even unified into one fundamental force. At this point, the universe spans a region of only 10 to 35 meters or 1 Planck length and has a temperature over 1032 Celsius. Grand unification epoch from 10 to 43 seconds to 10 to 33 seconds. The force of gravity separates from the other fundamental forces which remain unified, and the earliest elementary particles and antiparticles begin to be created. And the inflationary epoch from 10 to 36 seconds to 10 to 32 seconds. Triggered by the separation of the strong nuclear force, the universe undergoes an extremely rapid exponential expansion known as cosmic inflation. The elementary particles remaining from the grand unification epoch, a hot, dense quark-blown plasma, sometimes known as quark soup, become distributed very thinly across the universe. The electroweak epoch from 10 to 36 seconds to 10 to 12 seconds. As the strong nuclear force separates from the other two, particles interaction create large numbers of exotic particles, including W and Z bosons and Higgs bosons. The Higgs field slows particles down and confer mass on them, allowing a universe made entirely out of radiation to support things that have mass. And the quark epoch from 10 to 12 seconds to 10 to 6 seconds. Quarks, electrons, and neutrinos form in a large number as the universe cools off to below 10 quadrillion degrees, and the four fundamental forces assume their present forms. Quarks and antiquarks annihilate each other upon contact, but in a process known as baryogenesis, a surplus of quarks, about 1 for every million pairs, survives, which will ultimately combine to form matter. The Hadron epoch from 10 to 6 seconds to 1 second. The temperature of the universe cooled to about 1 trillion degrees, cool enough to allow quarks to combine to form hadrons like protons and neutrons. Electrons colliding with protons in the extreme condition of the Hadron epoch used to form neutrons and give off massless neutrinos, which continue to travel freely to space today. At or near the speed of light, some neutrons and neutrinos may combine into a new proton-electron pairs. The only rules governing all these apparently random combining and recombining are the overall charge and energy, including mass energy, we observe. And the lepton epoch, from 1 second to 3 minutes. After the majority, but not all, of hadrons and antihadrons annihilate each other at the end of the hadron epoch, leptons such as electrons and antileptons such as positrons dominate the mass of the universe as electrons and positrons collide and annihilate each other. Energy in the form of photons is the freed up and colliding photons in turn to create more electron-positron pairs. Nucleosynthesis from 3 minutes to 20 minutes. The temperature of the universe falls to the point about 1 billion degrees where atomic nuclei can begin to form protons and neutrons combined through nuclear fusion to form the nuclei of the simple elements of hydrogen, helium, and lithium. After about 20 minutes, the temperature and density of the universe has fallen to the point where nuclear fusion cannot continue. And the Photon Epoch, or radiation of domination. From 3 minutes to 240,000 years, during this long period of gradual cooling, the universe is filled with plasma, a hot soup of atomic nuclei and electrons. After most of the leptons and antileptons had annihilated each other, at the end of the lepton epoch, the energy of the universe is dominated by photons, which continue to interact frequently with the charged protons, electrons, and recombination and decoupling. From 240,000 to 300,000 years, as the temperature of the universe falls to around 3,000 degrees and its density also continues to fall, ionized hydrogen and helium atoms capture electrons known as recombination, thus neutralizing their electric charge. With the electrons now bound to atoms, the universe finally becomes transparent to light, making this the earliest epoch observable today. It also released the photons in the universe, which have fill this time with interacting with electrons and protons in a photon-wired fluid known as decoupling. And these photons, the same ones we see in today's cosmic background radiation, cannot travel freely. By the end of this period, the universe consists of about 75% hydrogen and 25% helium, with just traces of lithium. In the Dark Age, from 300,000 to 150 million years, the period after the formation of the first atoms and before the first stars is sometimes referred to as the Dark Age. Although photons exist, the universe at this time is literally dark, with no stars having formed to give off light. With only very diffuse matter remaining, activity in the universe has tailed off dramatically, with very low energy levels and very large time scales. Little of note happens during this period, and the universe is dominated by mysterious dark matter. And the reionization, 150 million to 1 billion years. The first quasars form from gravitational collapse, and the intense radiation they emit reionize the first surrounding universe. The second of two major phase changes of hydrogen gas in the universe, the first being the recombination period. From this point on, most of the universe goes from being neutral back to being composed of ionized plasma. The star and galaxy formation, 300 to 500 million years onwards. Gravity amplifies slight irregularities in the density of the primordial gas, and pockets of gas become more and more dense. Even as the universe continues to expand rapidly, these small dense clouds of cosmic gas start to collapse under their own gravity, becoming hot enough to trigger nuclear fusion reactions between hydrogen atoms, creating the very first stars. The first stars are short-lived supermassive stars, 100 or so times the mass of our Sun, known as population T or metal T. Eventually, population T and the population 1 stars also begin to form from the materials from previous rounds of star making. Larger stars burn up each time exploding massive supernova events. Their ashes go to form subsequent generation of stars. Large volumes of matter collapse to form a galaxy in gravitational interaction pulls galaxies towards each other to form groups, clusters, and superclusters. And the last one is the solar system formation, 8.5 to 9 billion years. Our sun is a late generation star incorporating the debris from many generations of earlier stars, and the solar system around it formed roughly 4.5 to 5 billion years ago. 8.5 to 9 billion years after the Big Bang, today 13.7 billion years, the expansion of the universe and recycling of star materials into new stars. How did the solar system form? Approximately 4.5 billion years ago, gravity pulled a cloud of dust and gas together to form our solar system. While scientists are uncertain of the exact nature of the process, observations of young stellar systems combined with the computer simulation have allowed them to develop three models of what could have happened so many years ago. The birth of the Sun. A massive concentration of interstellar gas and dust created a molecular cloud that would form the Sun's birthplace. Cold temperatures caused the gas to clump together, growing steadily denser. The densest part of the cloud began to collapse under its own gravity, forming a wealth of young stellar object known as protostar. Gravity continued to collapse the material onto the infant object, creating a star and disk of material from which the planet would form. When fission kicked in, the star began to blast a stellar wind that helped clear out the debris and stop it from falling inward. Although gas and dust showed young star in visible wavelengths, infrared telescopes have probed many of Milky Way galaxy clouds to reveal the natal environment of other stars. Scientists have applied what they see in other systems to our own star. After the Sun formed a massive disk of material surrounded it for 100 million years, that may sound like more than enough time for the planets to form. But in astronomical terms, it's an eye-opening. As the newborn Sun heated the disk, just evaporated quickly, giving the newborn planet in use only a short amount of time to scoop it up. The formation models. Scientists have developed three different models to explain how planets in and out of the solar system may have formed. The first one, and the most widely accepted model, core accretion, works well with the formation of the rocky terrestrial planets but has problem with giant planets. The second one is the pebble accretion, could allow planets to quickly form from the tiniest materials. And the third, the disk instability method, may account for the creation of giant planets. The core accretion model. Approximately 4.6 billion years ago, the solar system was a cloud of dust and gas known as solar nebula. Gravity collapsed the material in on itself as it began to spin, forming the Sun in the center of the nebula. With the rise of the Sun, the remaining material began to clump together. Small particles roll together bound by the force of gravity into larger particles. The solar wind swept away lighter elements such as hydrogen and helium from the close to universe, leaving only heavy rocky materials to create terrestrial worlds. But farther away, the solar winds had less impact on lighter elements, allowing them to pull speed into a gas giant. In this way, asteroids, comets, planets, and moons were created. The disk instability model. According to a relatively new theory, these instability clumps of dust and gas are bound together early in the life of the solar system. Over time, these clumps slowly impact into a giant planet. These planets can form faster than their core accretion rivals, sometimes as little as 1,000 years, allowing them to trap rapidly vanishing lighter gases. We also quickly reach an orbit stabilizing mass that keeps them from death marching into the Sun. As scientists continue to study planets inside of the solar system, as well as around other stars, they will be better understand how giants form. And the pebble accretion. The biggest challenge to core accretion is time. building massive gas giants fast enough to grab the lighter components of their atmosphere. Recent research probe how smaller pebble-sized objects fused together to build giant planets up to 1,000 times faster than earlier studies. And the water gathers. The solar system didn't ramp up its formation process after the planets formed. Earth stands out from the planets because of its high water content, which many scientists suspect contributed to the evolution of life. But the planet's current location was too warm for it to collect water in the early solar system, suggesting that the life-giving liquid may have been delivered after it was cooled. And the formation of the Earth. How did our planet Earth form? Our home planet is the third planet from the Sun and the only place we know of so far that's inhabited by living things. While Earth is only the fifth largest planet in the solar system, it is the only world in our solar system with liquid water of the surface. Just slightly larger than nearby Venus. Earth is the biggest of the four planets closest to the Sun, all of which are made of rock and metal. The name Earth is at least 1,000 years old. All of the planets except for Earth were named after Greek and Roman gods and goddesses. However, the name Earth is a Germanic word which simply means the ground. The size and distance of our Earth, with a radius of 3,959 miles or 6,371 kilometers, Earth is the biggest of the terrestrial planets and the fifth largest planet overall, from an average distance of 93 million miles or 153 million kilometers. It takes about 8 minutes for light from the Sun to reach our planet. The orbit and rotation. As Earth orbits the Sun, it completes one rotation every 23.9 hours. It takes 365.25 days to complete one trip around the Sun. The extra quarter of a day represents a challenge to our calendar system, which counts 1 year as 365 days. The structure of Earth is composed of four main layers, starting with an inner core and the planet's center, and followed by the outer core, mantle, and crust. The inner core is solid steel made of an iron and nickel metals about 759 miles or 1,221 kilometers in range, where the temperature is a high of 9,800 degrees Fahrenheit, 5,400 degrees Celsius. Surrounding the inner core is the outer core. This layer is about 1,400 miles or 2,300 kilometers thick, made of an iron or nickel fluids in between the outer core and crust in the mantle, the thickest layer. This hot, vicious mixture of molten rock is about 1,800 miles or 2,900 kilometers thick and has a consistent discardment. The outermost layer is crust goes about 90 miles or 30 kilometers deep on aviation lines. At the bottom of the ocean, the crust is thinner and extends about 3 miles, 5 kilometers deeper to the top of the mountain. The formation of the Earth. When the solar system settled into its current layout about 4.5 billion years ago, Earth formed when a gravity pulls swirling glass and dust into become the third planet from the Sun. Like its fellow terrestrial planets, Earth has a central core, a rocky mantle, and a solid crust. The Earth's surface. Like Mars and Venus, Earth has volcanoes, mountains, and valleys. Earth's lithosphere, which includes the crust, both continental and oceanic, and the upper mantle, is divided into huge plates that are constantly moving. Earthquakes result when plates screen past one another, ride up over one another, collide to make mountains, or split and separate. And the Earth atmosphere. Near the surface, Earth has an atmosphere that consists of 78% nitrogen, 21% oxygen, and 1% carbon dioxide. The atmosphere affects Earth's long-term climate and short-term local weather and shields us from much of harmful radiation coming from the Sun. It also protects us from meteoroids, most of which burn up in the atmosphere, seized as meteors in the night sky before they can strike microphase of meteorites. The magnetosphere. Our planet's rapid rotation and molten nickel iron core give rise to a magnetic field, which the solar wind distorts into a teardrop shape in space. The solar wind is stream charged particles continuously ejected from the sun. When charged particles from the solar wind become trapped in Earth's magnetic field, they collide with air molecules above our planet's magnetic poles. These air molecules then begin to glow and cause aurora or the northern or southern lights. The formation of moons. Earth is the only planet that has a single moon. Our moon is the brightest and most familiar object in the night sky. In many ways, the moon is responsible for making Earth such a great home. It stabilizes our planet's wobble, which has made the climate less variable over thousands of years. Earth sometimes temporarily hosts orbiting asteroids or large rocks. They are typically trapped by Earth's gravity for a few months or years before returning to an orbit around the Sun. Some asteroids will be in a long band with Earth as both orbit. Some moons are bits of rock that were captured by a planet's gravity, but our moon is likely the result of collision billions of years ago. When Earth was a young planet, a large chunk of rock smashed into it, displacing portion of Earth's interior. The result chunks lumped together and form our moon. With a radius of 1,080 miles or 1,738 kilometers, the moon is the fifth largest moon in our solar system. And the very important potential for life. Earth has a very hospitable temperature and mix of chemicals that have made life possible here. Most notably, Earth is unique in that most of our planet is covered in water. Since the temperature allows liquid water to exist for extended periods of time, Earth's vast oceans provided a convenient place for life to begin about 8.8 million years ago. Thank you for watching this video and I hope you enjoy, and please share this to your loved ones for them to be able to know the formation of the universe